Hi everyone, and thank you for joining this session. I'm Narendra Reddy Mudiyala. I work as senior data engineer with 7 years of experience, specialized in building high performance, scalable data solutions that connect innovation with real world impact. My focus is on architecting systems that can handle massive data volumes without compromising speed, reliability, or flexibility. I'm passionate about exploring emerging technologies that push the limits of what's possible in modern data infrastructure. That's exactly what brings us here today to explore how Rust, paired with data mesh principles, can completely reshape the way we think about large scale production grade architectures. In this session, we'll talk about how Rust can transform modern data architectures by applying data mesh principles. We will explore why enterprises need to move away from monolithic systems, how Rust's memory safety and fearless concurrency enable high performance, reliable pipelines, and real world implementations. We'll also look at benchmarks, advanced Rust patterns, and strategies for integrating with cloud infrastructure to build scalable, future ready data platforms. Let's get started. We are all aware of how rapidly data is growing. It's exponential. The problem is that monolithic architectures can't keep up anymore, and we end up with bottlenecks and inefficiencies. That's why moving to distributed system isn't just an option, it's essential. Distributed systems give us the scalability and flexibility we need to manage these massive data demands. This is where data mesh comes in, a decentralized approach that puts data ownership in the hands of domain experts, improving collaboration, reducing dependencies, and scaling more effectively. So, why first memory safety? RUT's ownership model means no data races and let us write robust concurrent processing code without sacrificing performance. Then there are zero cost abstractions, which let us write expressive high level code without any runtime penalty. Finally, fearless concurrency. Rust makes parallel processing safe and reliable, which is absolutely critical for high throughput data pipelines. When we talk about performance, Rust truly stands out. One of the biggest gains I've seen is in data processing speed. Using Rust's asynchronous runtime, we can achieve up to 10 times faster processing compared to many traditional solutions. That's not just a small optimization. That's the difference between a job finishing in hours versus minutes. Another huge advantage is building memory safe pipelines. Because of Rust's strong type system, a lot of the bugs that would normally show up at runtime, things like null pointer errors or data mismatches, simply can't happen. This means fewer production incidents and much more reliable systems. And then there is stream processing. If you have worked with JVM based solutions before, you will know they can be powerful but also heavy. In real time analytics, Rust outperforms them, delivering low latency and higher throughput. That means we can process streams of events faster, react to changes more quickly, and do it all without consuming excessive resources. In short, Rust gives us speed, reliability, and efficiency all at once. And those are the three pillars you need for any modern high performance data pipeline. Let's move from theory into practice. When we're actually building high performance data systems in Rust, there are few tools and techniques that really make a difference. First, asynchronous processing with Tokyo. Tokyo is a high performance asynchronous time that lets us handle massive amounts of concurrent work without blocking threads unnecessarily. In a data pipeline, this means we can process incoming requests, transform data, and push results downstream, all in parallel without choking the system. Next, zero copy serialization with Cerde. In many systems, serialization and deserialization are bottlenecks because you are constantly copying data in and out of memory structures. With Cerde, you can avoid those extra copies, which not only improves the performance but also reduces memory pressure. This is especially powerful when you're transforming and transmitting huge data sets. And finally, columnar data operations with Apache Arrow. Arrow lets us store and process data in a columnar format, which is far more efficient for analytical query. In my experience, combining Rust with Arrow means we can run high speed analytics on large data sets that would otherwise be more traditional row based storage systems. When you put all of this together, async processing, zero copy serialization, and columnar data operations, you get a data pipeline that is extremely fast and resource efficient. This is where Rust really starts to shine in real world scenarios. So now let's talk about building the infrastructure that supports these high performance pipelines. For me, starts with the high throughput Kafka consumers. I use the RD Kafka RS library, which is a Rust wrapper from the battle tested Kafka C library. It gives us reliable, low latency message consumption at scale, which is perfect for ingesting millions of events per second without dropping messages. Then I focus on memory efficient transformations. Rust iterators and zero allocation patterns are game changers here. Instead of creating temporary objects that clutter up memory and put pressure on the garbage collector, which Rust doesn't even need, then stream transformations directly, keeping memory usage minimal and performance high. Finally, I think about robust HTTP APIs. When we need to expose data or services to other systems, I like using frameworks like Action along with Tower middleware. This combination let me build APIs that are fast, secure, and easy to integrate into wider data ecosystem. Plus, since these APIs are written in Rust, they inherit the same performance and safety guarantees as the rest of the pipeline. All of these pieces, Kafka consumers, efficient transformation, and strong APIs, work together to create an infrastructure that isn't just fast, but also resilient and scalable for long term growth. Performance benchmarks. So, whenever I talk about Rust in data systems, one of the first questions I get is how does it actually perform compared to Python, Java, or Scala? So, I make it a point to run real world benchmarks, not just synthetic tests. I take actual data workloads, the kind you would see in production, and compare implementations across these languages. Every time, Rust consistently shows lower latency, higher throughput, and better resource efficiency. The tools I use for these benchmarks are well established and reliable. They measure not just speed, but also memory usage, startup times, and consistency under load. This isn't about proving that one language is better in all cases, but about having accurate performance insight so I can make informed architectural choices. And the impact is huge. These benchmarks directly influence system design decisions. For example, if certain part of a pipeline is performance critical, real-time event processing or data transformations on massive data sets, Rust often becomes the clear choice. By contrast, for less time-sensitive components, another language might make sense for speed of development ecosystem support. In short, benchmarking keeps us honest. It ensures that we are picking the right tool for the job. And more often than not, it highlights where Rust can give us a major advantage in high performance data processing. Now we have covered performance in infrastructure. I want to share some advanced Rust patterns that I have found especially valuable when building large scale distributed data system. First, actor model implementations. I like using the actor model to isolate domains within a distributed system. Each actor has its own state, communicates through message passing, which not only improves modularity, but also makes the system much easier to scale. In Rust, this model is both safe and efficient thanks to the language's concurrency guarantees. Second, custom derived macros. In big projects, I often need to enforce certain rules consistently across the code base, like validating the incoming data structures. With custom device macros, I can automate that. It means every developer on the team gets validation for free without having to remember to write it manually. And it keeps the code base clean and uniform. And finally, WebAssembly for security. This is where Rust flexibility really shines. I can compile parts of the REST application into WebAssembly modules and then run them in a sandboxed environment. That's perfect for crossing data across different domains and even different organizations because the isolation gives me an extra layer of security without giving up performance. These advanced patterns, actors, macros, and WebAssembly gives us the ability to build systems that are not just fast, but also maintainable, secure, and ready to evolve as requirements change. For me, a high performance data system isn't complete unless it integrates seamlessly with a cloud environment it's deployed in. Rust makes this easier than you might think. Start with seamless cloud integration. Whether I'm deploying on Azure, AWS, or GCP, REST applications can hook into existing cloud services with minimal overhead. I can connect to managed databases, storage systems, message queues just as easily as I can work with on prem components. That means I get the flexibility to run in hybrid or multi cloud setups without rewriting large parts of the system. Next, we look at microservices architecture. Rust is great for building small, focused services that do one job extremely well. When each service is independent, I can scale them individually based on demand, scaling the ingestion layer without touching the analytics layer, for example. Approach also makes maintenance easier because the teams can work on different services without stepping on each other's toes. And finally, data contracts enforcement. This is one of the Rust's hidden superpowers. By defining strict data structures and enforcing them at compile time, I can guarantee that data exchange between services always in the correct format. This eliminates a whole category of runtime errors and reduces the need for defensive coding. When I combine these capabilities, cloud integration, microservices, and compile type data contracts, I get a cloud ready architecture that's efficient, safe, and designed for the long haul. As we wrap up, I want to bring the big picture back into focus. For me, Rust isn't just another programming language, it's a game changer for how we approach data architectures. By combining Rust with data mesh principles, I've seen firsthand how we can build infrastructures that are both highly scalable and rock solid in reliability. Looking ahead, the Rust ecosystem is evolving fast. We are seeing improvements in async runtimes, new libraries for data processing, and even more seamless integrations with cloud platforms. All of these developments means the Rust is only going to get more capable for handling the toughest data challenges. My takeaway for you is this. If you are working on systems that need to handle massive data volumes, low latency, and high reliability, Rust should be on your shortlist. Gives you performance with sacrificing safety, without sacrificing safety, and scalability without the typical complexity overhead. And I will leave you with a call to action: explore Rust. Try it on a small, high impact part of your pipeline, see how it performs in your environment. You might be surprised at just how much of a difference it makes. This concludes my presentation. Thank you for your time and attention. Have a good day.